Right, so today's session we'll have an introduction, programming introduction to NumPy, numerical computing in Python. So before that, we'll have a look at the different shells, the different interfaces for Python programming. Everyone please, can you turn off your laptops? You don't need a laptop today. So in the previous course, I believe we had worked on Replit-like platforms, or we had used the Python shell interface, which might have been something like this. So you get this interface and you would type something. So you'd get your responses to the code that you're writing. Now, similar to this, there are some enhanced interfaces, one of which is known as IPython. Now, it gives you various advantages such as autocomplete. You can use the history here. So it's again an interactive Python terminal, enhanced interactive Python terminal as it is mentioned. But for most purposes, we would be using the Jupyter Notebook, which is a web-based interface for writing Python code. Now, when we mention web-based interface, the backend or where the Python computations occur, where all of these computations occur, is still on the backend. It's still not on the web interface. So it's not some JavaScript code which is running. It's still the web browser is acting as an interface. So the command which we run after we've installed Jupyter Notebook is to run this command called Jupyter Notebook. This will open something in the web interface which shows the different notebooks which I have in this folder. So this is one way in which we can write Jupyter Notebooks. One of the important reasons to write Jupyter Notebooks is, apart from the fact that it is giving you an enhanced interpreter, you also get something which you can share easily over the internet. Like, as an example, if I open this notebook stored on GitHub, I go to the PhDV notebooks, I click on notebook and intro NumPy notebook. This is the same notebook I'm running today. So you can see this nicely rendered on GitHub. We could have also chosen some other renderers for this notebook. So it can help us create very simple notebooks which illustrate some concepts, and in very easy, accessible, reproducible fashion, we can share these notebooks with different people. So this is one such interface which we could use to run and execute Jupyter Notebooks. We could also use Visual Studio Code. So I've installed Visual Studio Code and I've installed its command line extension. So therefore I can just write code dot, which opens Visual Studio Code in the current directory. And you can see the same notebooks here. I can run them, I can change, I can edit, etc. For today's lecture, I'm not going to use Visual Studio Code. I will be just using the browser extension, the browser version Jupyter Notebook. Or the third one is to use Google Colab, which you can think of as Google Docs, but for writing Jupyter Notebooks. So here also you can create a new notebook from scratch. You can also use GitHub. So you can also open different notebooks on Colab. But as I mentioned, for today's lecture, I'll be using Jupyter Notebook interface on the browser. So I'll open this notebook. This particular notebook is very heavily inspired from this wonderful textbook, Python Data Science Handbook. So if you search Python for Data Science Handbook by Jake Vanderplas, this is heavily inspired from that, which includes NumPy, Pandas, Matplotlib, some amount of machine learning. So we are borrowing heavily from this. Now, before we run into NumPy, we understand the syntax, the different commands, the different utilities. I just also want to show you why we are bothering about using NumPy. So when we think about computers and the way they store data, they always store data in the form of various kinds of numbers or various kinds of arrays. So we'll look at a few examples now. In this particular example is the code is the code size good enough? Can you see it clearly? Okay, made it slightly bigger. So in this particular notebook, I am loading a few modules: NumPy, PIL, Python image library, matplotlib for plotting, matplotlib inline, and I am using this particular code to just make the plots sharper. I am opening a data set, an image which is stored locally. It's called street.jpg. You don't need to bother about all the syntax for now. We'll cover when we need it, we'll get there. So this is showing you an image which I have read in some NumPy array. Again, we'll see what this NumPy array is, etc. But I am plotting this particular image. I'm showing you this particular image being plotted. Now, how do you think this image is stored in a computer? So this particular image, if we look at the underlying data structure, which is called image array, and we just print it out, so you can see that this seems to be a bunch of numbers. What can you observe about these numbers? Sorry? These are RGB values, but what can you observe about these numbers? Can you observe their data type? Are there integers, floats, binary? They seem to be integers. Can you see the ranges? What is the range of these numbers? They seem to be between 0 and 255. None of them is exceeding. As well as you can see that there is some, it looks like a list within a list within a list, like structure. So it seems like a 3D list kind of a structure. So list from the previous semester where you studied Introduction to Programming. So this is indeed a 3-dimensional array. So therefore, in order to store this image, we need 3-dimensional array, where the 3 dimensionals, the sizes that we see of this particular image, they are 2000, 3000, and 3. So can you observe that is this image wider than it is longer? Yes. So therefore, what it is saying is that we have 2000 pixels going from top to bottom, 3000 pixels going from left to right, and then there are 3 numbers corresponding to each such pixel. Right? So if we were to understand this slightly in a different fashion, let's assume that we have this as our image. So you have the rows going down, you have the columns going from left to right, and then you have some values stored in each pixel. Just that here we are storing 3 values in each pixel. So it would be something like, let's say this is 10, 20, 30. This is, let's say, 20, 40, and so on and so forth. So these are my row 1, row 2. Let me start from 0 indexing, row 0 through row 21. And this is my column 0 to column, let's say, 6. So this is how we are storing this image. Importantly, in each cell, we are storing 3 numbers, which corresponds to the RGB representation of this image. Red, green, blue. So this first number is storing the red pixel value, the green pixel value, the blue pixel value at the first row and the first column. So therefore, it's important to understand that in order to represent this seemingly simple image, we need an array of numbers. In this case, we need a 3-dimensional array of numbers corresponding to the height, the width, and the 3 colors, R, G, B. We also saw that the data type of this array of the numbers stored here is an integer 8. So it's going from 0 through 255. Now, once we have stored such arrays, we can do a lot of manipulation for our own purposes. I believe all of you are using some kind of social media app, some kind of good camera apps where you're doing various kinds of filters. Now, all those filters are nothing but simple manipulations of this particular data which is stored here. So let's say if I had to rotate this image by 90 degree counterclockwise, so I can call this very simple one-liner Python code, numpy.rotate 90, this image array, and now you can see that it's been manipulated. So therefore, all the complicated software that you might be using, let's say Photoshop or movie editing software, under the hood, the data is stored in this particular format only, in some kind of array format only. And NumPy is a very good Python package to work, Python library to work with such multidimensional arrays. We could have also done various kinds of manipulations. So we can get the 0th row, 0th column, 0th row, 0th column. We'll get a 3-dimensional vector. So we get a 3-dimensional vector which corresponds to the red, green, and blue value. We could do various other kinds of manipulations also. For example, I have now set in this image, if you notice, this part, the first quarter, looks to be significantly more red compared to the other 3 quarters. So this is again a very simple 2-line Python code. I extract out this quarter of the image. I make the red value as the maximum possible red value, which is 255. Again, don't bother about understanding all of the syntax immediately. We'll get to it in a few minutes. This is just to show you that for many modern computer applications, you need to store the data, store the different kinds of objects. In this case, I've shown you an image which is stored as a 3-dimensional array, the height, the width, and the 3 numbers corresponding to the red, green, and blue. Now, similarly, if I have to open some kind of an audio, how do you think an audio might be stored? How might a computer store an audio? So again, the computer has to store it in a sequence of some numbers. The images were stored as some 3D array. In this case, if we look at this audio, so let's first play this audio.
The Prime Minister of India is Narendra Modi.
Now, if we... Okay, for some reason the notebook restarted, I think. Now, this is how the waveform is looking like. Is this now looking somewhat similar to familiar? You have this audio waveform, you have the amplitudes, and maybe these are the places where we have some silence, and this is where the amplitude is high. So this is the audio waveform where we have the amplitude versus the samples. Now, if we are to look at this array, can you again see it seems to be now a 1D vector, very large, very long 1D vector containing some zeros and some numbers. In this case, you might be thinking that it's only zeros. It's actually not only zeros. It's just that the starting few samples are zeros and the ending few samples are zeros, and this is just showing you a compact representation. It's not showing you the entire representation. So therefore, to store audio files also, you need some sequence of numbers which you need to store. I would call this as a 1D array, or in mathematics, you might have learned this as a vector. So images, you can think of this as 3D arrays. In this case, audio, you can think of it as a simple 1D array or a vector. We can extract various kinds of information from it. In this case, it tells us that there are 82,368 samples, and we also note the frame rate is 24,000 frames. Often it's important to not get amplitude as a sample, but to get amplitude as time. Like in this case, we have the audio play in the time domain, not really in the samples domain. So we can again do some manipulation. You know the total time, you know the frame rate. So you'll get the total number of seconds. This is the total number of elements, 82,368, divided by the frame rate, 24,000, you'll get about 3 seconds. That's the time. And then you can, again, just plot that. So, by the way, these different things which you're seeing in the Jupyter Notebook, these things are known as cells. And I'm running them. You could run them via clicking on the UI. Like I can move my cursor here and then click on this run this cell and advance. And you can also see the shortcut that they're showing, Shift and Enter, which is what I'm typically using. So I don't use my mouse a lot while using Jupyter Notebooks. So thus far we have seen two different kinds of data which we often require. One is an image, another is an audio. Both of them are stored as arrays. Okay, I again don't know if there seems to be some cross interference. So now we have seen two different kinds of objects which we commonly use. We could have also stored videos. Now how do you think we'll store videos in a computer? Will they again be an array? Video can be thought of as a sequence of images, so you can add another dimensional to the array, which can be the time dimension. So, for example, let's just summarize our findings here. So we have, let's say, SNO and the object and the shape. One of it is an audio. So its shape is generally n. It is a vector of length n. We can have a grayscale image. Grayscale image means it has a single channel. So here the channels correspond to the height, width, and just and then we store the numbers there. We can have a colored image whose dimensions are height, width, and then the vector corresponding to RGB. We can have a video where we can have the time dimension, we can have the height, width, RGB if it's a colored video. So therefore we can see that in all these cases we have some multidimensional arrays. Right? So we can see this colored video is an array or a sequence of images. So therefore we need some data, some libraries to efficiently handle these kinds of multidimensional arrays, and NumPy is a very well written library for this case. Once we have these audios, we can also do, and on the image I showed you different kinds of transforms. Similarly for the audio we can have different kinds of transforms. Like I can apply some simplifying filters which smoothen out the audio. So if this was the original audio,
the Prime Minister of India is Narendra Modi.
And this is the audio which has been filtered.
The Prime Minister of India is Narendra Modi.
The effect is not very good, but I just wanted to show you that you can write some very simple lines of Python code and get some filtration. And then even with text, you can do a bit of extraction. You can also represent text as a sequence of numbers. For example, for this case, we represent this as this particular text: the quick brown fox jumps over the lazy dog, never jump over the lazy dog quickly, as again some set of vectors. So the important question here now is, we have already studied Python list in the previous course. They are a very popular data structure, inbuilt data structure. Why not just use Python list for our purposes? Any thoughts on that? Python lists are slow. Okay. Any other answers?
So Python list allows us to have different types of data types.
All right. So Python list can be heterogeneous. As a consequence, they can often be slow. So this is again a very nice. Where did the image go? Okay, the image is not appearing, but let me show from here. So Python list can contain heterogeneous data types, which mean you can have an integer, a float, a string, and various other data types within a Python, even a list within a Python within a Python list. So therefore, the way Python lists are stored in the computer memory is that you have this head, you have the length, and then you have the items. These items are effectively a collection of the memory locations. These are the computer memory locations. And these memory locations, the data is stored. Like one of the data could be a string, the other could be an integer, something else could be something else. So for each of them, you need to have some kind of a representation telling what that specific object is. So therefore, these data, if you can notice, are not contiguously stored. They're not stored one after the other. Whereas NumPy has this inherent advantage that we say that we will only be using the exact same data type for all the objects in that list. So therefore, it does not need to store the memory locations for each of the individual object. It knows that there is a constant offset for each of the elements stored in that list. So that's one advantage which NumPy gives you, and because of which it is often very quick. So we can check that here. We are using a Python list and doing this particular operation, which is we are squaring every number in this list, which is a list of numbers from 1 through this huge number. So we are using this concept of list comprehension, which you might remember from the previous course. I'm starting the timer before I do this operation, and I'm ending the timer after I'm done with this operation. So this will take me some amount of time, and I'm using f strings here, just as a quick revision for you. Whereas if I were to do the same thing using Python, using NumPy, so if you notice, the syntax is much more succinct. I just need to write array into square, which means that every element in that array would be squared, and I look at the time. And if I execute this, the Python list computation time took 0.33 seconds, whereas for NumPy it took just 0.2 seconds. So NumPy is significantly quicker than Python for such kinds of operations whenever you're doing any kinds of manipulations. So one advantage which NumPy has over Python is the fact that the data is all homogeneous, which means all of the same data type, and therefore the storage is also much more efficient. The other is that many such operations which are happening in the Python layer in the case of list can happen in the compiled code, which is often written in C or Fortran in the case of NumPy, so which makes it execute quicker. Now, this was just to whet your appetite and show the possibilities which exist in NumPy and why to use NumPy. Now we'll do a very quick tour of NumPy and what to expect and what are the kinds of operations we can do. The first thing which I always do before I start any notebook is to print out the versions. The version of NumPy that I'm using. So I'm using import NumPy as NP. You're importing the package. You will use this NP as the name wherever you want to use NumPy. It's shorter. It's the most commonly used line whenever you're using NumPy. And we are using this particular line to print out the version. Oftentimes when people say that their code is not working, someone else's code is working with us, the code is the same, you want to ensure that the NumPy version and the other library versions are the same. So this will help you with debugging. Now, so we already know how to create lists. Okay. We know how to create lists in pure Python. The creation of lists in NumPy is also fairly easy, but there are different ways in which we can do that. For example, if your Python list was 1, 2, 3, and 4, you can call np.array on the Python list which has been created, and you would get something known as, so if you print PyList, you get 1, 2, 3, 4. Whereas if you print it seems to be the same thing, but they are different objects. So if you print out type of PyList and you print out the type of from list, you'd see the first one is a simple Python list. The second was a numpy.nd array, which means n-dimensional array. Therefore, while they're seemingly similar, but they are different storage. They are different kinds of objects being stored. Now, often we want to create different kinds of NumPy arrays. Like whenever you'll use machine learning, whenever you'll use arrays in machine learning, you'll often end up using different kinds of matrices and arrays. Some of them are vectors, some of them are the zero vectors, some of them are the zero matrices, some of them are the identity matrices. So therefore, NumPy provides you different ways of creating those. Like if I wanted to create a list, NumPy arrays of zeros with just using the above syntax. So I could have done py list equal to 0, 0, 0, 0, 0, 0, 0. Something like this, and I could have done np dot array of py list, and it will print this particular array. Or I could have done zeros arr to np dot. Did you see what I did? You probably might not have been able to notice. So I did np dot ze. I press tab on my keyboard. It gives me various functions under the scope of NP which start with ZE. So they are zeros, zeros are zeros like, so on and so forth. So I very often use this because this can help you understand the API. If you forget different functions, you can again do a quick reference. And sometimes I do this just to explore. So let's say if I just did NP dot and I press tab, it shows me different kinds of things which are possible. Shows ABS, absolute, ACOS, ACOS-H, add. So I would often try and explore this and see the different kinds of functions, instances, class, modules which are available, and get to know more about the API. For now, I will just do numpy.zeros. I know that there is this function which is used to create an array of zeros, but I don't know how to work. I don't know how it works. So then I will use my other favorite tool, is to put a question mark. And I press shift enter, which is I ran the cell. Now it immediately gives me the documentation. It tells me that this is a function np.zeros, which takes an argument as the shape, the d type, the order, and some other arguments, and like equal to none. So it tells me that the parameters are shape, which is the shape of the new array 2, 3 or 2. The d type, which is optional, the default is NumPy, is float 64. The order is column C style or the column major style, Fortran style. So most cases we'll just use the defaults. Now I get a sense of I need to pass in the shape. Now, if I were to give np.zeros of, how many do we have? 1, 2, 3, 4, 5, 6, 7. So this complete, tab complete also works in other scope also. So I had this ZE, I did a tab complete. Instead of typing out in full, this ensures that I don't make different kinds of typos. Can you see that these two things ended up being similar? But they're not exactly the same. What is the difference? The first one seems to be float. The second one seems to be integers. So we could have also looked at the documentation and we saw that d type equal to float was an option. Okay, what does it say? We can give int 32. Okay. Can you now see that they seem to be both integers? So therefore, this is not just to show you how to learn NumPy, it's also just to show you how we can think about learning different libraries. This is just one specific library. You can use the same techniques for learning other kinds of libraries also. So now we have created a vector of all zeros. We could have also created a matrix of zeros where the matrix size is 2, 3. 2 rows, 3 columns. Now this is created, if we look at the output of this particular lines of code, it has created me a 2, 3 dimensional matrix. So it has 2 rows and it has 3 columns. So this is equivalent to the entry being 2 rows and 3 columns. Can you see this is the 2 row and 3 column matrix? This is exactly what we have here. 2 rows, 3 columns. Similarly, we could have had a 1D arrays of zeros. Now, we have looked at one particular instantiation of creating arrays, which is from Python list, the other being creating a NumPy array of all zeros. Similarly, there is a NumPy arrays of all ones. So we can create a NumPy arrays of all ones of the matrix size 3, 2. So this is the shape which we are passing. If you remember the argument to numpy.zeros and similarly to numpy.ones, we have to pass a tuple of the shapes. This is a tuple of 3, 2. So therefore this array is of size 3 rows, 2 columns. There are other very useful functions which we want to create. So we had the range function in Python. We have so using this range function, we can create these different ranges of numbers in some steps. So go from 0 through 10, before 10 in steps of 2. That is in pure Python. We have a NumPy equivalent, which is numpy.arange, goes from 0 through 10 and steps of 2. So just before 10 it stops. The advantage of this over the Python version is that you can also do various kinds of other steps also. So you can very conveniently give these different steps here also. Now, one place where we often end up using such kind of functions, which is numpy.arange, is while making some kinds of plots. We'll study this properly when we study matplotlib, but just to whet your appetite. So let's say if I have a function which is sine of x. I want to understand how this function looks in a range of 0 to 2 pi. So in that case, I would do my x range equal to np.arange of 0 to 2 into np.pi and a step of 0.01, and my y equal to f of x range. I can now call this function on matplotlib. Okay, I think I made a mistake. X range. What is our X range? X range looks okay. What is our Y? Y is none, because I was not returning anything in the function. Now this is, both of these are correct. This is to show you how you can go about debugging. And now if I were to plot this, you can see this function, which is the sine function plotted from 0 through 2 pi, in where the gaps, these gaps that you're seeing, are 0.01. If these gaps were to be made larger, you can see that this waveform will look a little jagged. Not so much observable now, but let's say this was 0.5. Can you now see? Because we have fewer points on the x-axis, correspondingly fewer points on the y-axis. If this were made even, the gaps were made even larger, you can see that this making a very poor approximation of this function now, because we have taken very small gaps, very large gaps. We could have also taken very, very small gaps, in which case this curve will look very smooth. So that is one of the places where we very often end up using the numpy.arange function. We have a similar function, linspace. So it creates an array where the entries are linearly spaced between the starting and the ending entry, and we have this number of entries in that. So for example, we want 5 entries between 0 and 1. it will automatically figure out that what should be the gap between these entries. In A range, we had to ourselves specify the gap between entries, and in length space, we don't have to specify the gap, but we specify the number of entries. So you can get similar output using both of these functions. Similarly, when we want to create an identity matrix, so this has created np.I of 3 creates an identity matrix of size 3 cross 3. Any questions thus far? Okay, so we have created these different arrays. Now we want to explore the API a bit further and understand that what are the different attributes which are available for these different arrays. Attributes means what are the different properties that these arrays have. Some of the important ones are the shape. Shape, as in we have seen this kind of like we have seen that an audio will be of the shape of like a vector. So it will have a shape just. Okay. Unfortunately, there seems to be some interference. The audio will have a single dimension. The grayscale image will have dimension 2. Colored image will have dimension 3. Colored video will have dimension 4. The shape of this could be n, this could be h, w, this could be h, w, 3, and this could be t, h, w, 3. So that would be the shapes of these different kinds of objects or these different kinds of arrays. Now, in this case, I am creating a random array containing random integers from 1 to 10, and the size of this array which I am creating is 3, 4. So we should just print out this random array. This random array is of size 3, 4, which means 3 rows, 4 columns. And all of the numbers are integers randomly chosen between 1 and 10. Oh, we were anyway printing here, I think. Now, if we look at the random array.shape, this is 3, 4, so which is similar to what we're seeing here. So it's telling you the different dimensions and the number of entries across each dimension. The size is the total number of entries. So you can think of the size as just the product of the different dimensions, or in this case the total number of entries 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The number of dimensions is 2, and the data type which we have, which is stored in random array.d type, is int64. So therefore these are the properties .shape, .size, .endim, .d type. So I've already showed how to take help using question mark and .tab. You could have seen other possible attributes also. Like we have, if a is equal to np.zeros 2, 3, I want to look at all the possible things which are there in a. So if I do a dot, it gives me that there are these different attributes and things which exist. A.size. So A.size is 6 because the total of entries is 6. Now, one thing which people very often get confused when using NumPy for the first time is the difference between these two shapes. One is called n comma and the other is n comma 1. So if I create this array of size of 3 elements which are all zeros, and if I look at the shape of it, so do a equal to np.zeros of 3, and I look at the shape, versus I give np.zeros of 3, 1 versus I give np.zeros of 1, 3. So the latter two cases, B and C, they are taken to be matrices. B is the matrix. You can very clearly see it's a matrix of 3 rows and 1 column. Whereas C is a matrix of 1 row and 3 columns. Whereas A, you can see that it has a single square bracket only. So it's considered to be a vector of size 3. It's an important distinction. Oftentimes we end up making mistakes in the shapes. 3, 1 is not the same as 3 is not the same as 1, 3, even though the entries, the elements stored in all of them are the same. We need to very importantly consider the first one is a vector, B is a matrix of size 3 rows, 1 column, and C is a matrix of size 1 row and 3 columns. Now, very often, we want to not just use the arrays, just create the arrays, but we want to create some operations on those arrays. Like in list, we want to subselect some items in a list. Similarly, in arrays, we want to subselect some items, some get to aggregations, etc. So we also did this operation a few minutes back when we were looking at this particular image. So here, in order to make the first quarter more red, we had to first choose the first quarter. Now, how would we choose the first quarter? Can we see that the first quarter is composed of the first half of the rows and first half of the columns? So you have to consider the first half of the rows and first half of the columns, and therefore, and with that area, you will get the first quarter. So therefore, you have to do some selection into this, or you have to create an index into this and then do some manipulation around that. Now here we have an original array, which is a 2D array. The size of this array is, you have 3 rows, we have 3 columns. So it's a 3 by 3 matrix, or it's a 2-dimensional array where the 2 different dimensions are both 3 and 3. The indexing and slicing are fairly common, fairly similar to what we had in Python list. We can typically access a single element. So let's say we want to access a single element, this particular element. Can we see that this particular element is the 0th row and the 0th column? So therefore, in order to access that, we can give x of 0, 1. X is this multidimensional array. We first give the, if we want to get the, so if we want to get 20, then it is the first row and the second column, which means the 0th row and the column number 1, because we start with 0. So therefore we get x of 0, 1, and the output we get is 20. Now very often you might get a natural question, especially coming from Python list, that why not just do x of 0 and then get the first element of it? X of 0 will give you this particular row, this particular set of values, and in which if you get the first element, it is 20. So both of them seem to be giving you the equivalent answer. But when we're using NumPy, you should always prefer to use the first method because it's much more efficient. The second method will first create a temporary array which contains the value 10, 20, 30, and then it will create an index into it, which will give you the value 20, whereas the method x 0, 1 will directly give you this particular value. Now, we can also create different kinds of slices. These slices are also something you have seen in the course, in the Introduction to Programming course. In indexing, you are choosing some specific value only, some specific index only. In slices, you are choosing some contiguous set of values. So you can choose x of colon, 1, which means you will slice up to the first row. So if this was x, 10, 20, 30, 40, 50, 60, 70, 80, 90. So if you select up to the first row, you will just get this first row and you'll get all the columns. Okay, let me print. Okay, I'll come to that again. Whereas if you had written x of 1 colon, it starts slicing from the second row and everything after that. So x of 1 colon will give you 40, 50, 60, 70, 80, 90. It will start from this point and give you everything below. And if you give x colon colon 2, it will select every alternate row. 10, 20, 30, 70, 80, 90. Some of you might have got confused as to what is happening with the columns here. So it's important to note, when you're not giving anything in the columns, it will pick up all the columns. I would suggest that when you're starting out, instead of writing like this, you write something like this, which means you need up to the first row and you need all the columns. Similarly, you want to start from the first row and you want all the columns. And similarly, you want to choose every second row and you want all the columns. And you can verify that the answer that you're getting is exactly the same as you got earlier. But just that this is making your life slightly simpler because you're always giving row and column, row, comma, column, row, comma, column, row, comma, column. Any questions thus far? Okay. So another important caveat, another place where I've seen students often make a lot of mistakes is understanding that what happens if I were to make some changes to a sub-selected or an indexed array. So to understand that, I create this array. By the way, I'm using some shortcuts. So this particular notebook is also known as a modal editor. There are different kinds of modal editors, like Vim is a very commonly known modal editor, which means you have two modes. One mode is where you're running the commands. The other mode is where you're editing the text. So if I press escape, I can alter the mode. So therefore, I'm without even using the cursor, I often change the mode. And in this case, I created a new cell above. And after that, I cut a cell and I pasted it above, just to make it slightly more convenient for you. So you can see that this is some 2D array of size 4, 5, 4 rows, 5 columns. Now, I have done an indexing into this. I am choosing the first 2 rows and the first 3 columns. So the first 2 rows will give you these entries and the first 3 columns. So you're effectively looking at 3, 8, 8, 8, 4, 3. And that is what you get in this sub-array. This particular variable, sub, is now pointing to this particular sub-array. Now, if I were to make some change in this sub, in this specific object, sub, it's 0th entry. What is the 0th entry? Currently 3. If I were to set it to 99, and if I were to print out the original array, which is array 2D, you'll see that the original entry is also manipulated. It's also changed. Right? This is an interesting observation, that if you're modifying some sub-selected array, it is also modifying the parent array from which this data sub-array was borrowed. So this is a consequence of this sub-indexing being a view of the original array. It is not creating a copy, but it is creating a view in it. View means that it is still pointing out to the same location. It is pointing out to the same data, and if you make a modification here, it will get reflected in the main because it's pointing to the same memory location. I've seen students very often make mistakes in these kinds of things. Rather, if you want that the original array remain unmodified, we'll create something known as a copy of the original array. So everything else before, but here I make a change. I do array 2D, first 2 rows, first 3 columns. I do a dot copy, which creates a copy, which means that this will now be a new object, which means it will be now pointing to a new memory locations, which means that the previous array and this array are now independent of each other. You can make any manipulation in one without affecting the other. Now in this, if in this array 2D copy, I modify the 0th location and set it to 99, you can note that the changed copy becomes 9942 and 921, whereas the original array remains the same. One place where you very often end up using such kinds of operations are, let's say, for audio manipulation. So if you use any audio software or if you use any video software, very often you want to clip some time segments which were noise. Like if I were to do a quality screen recording for today's lecture, I may want to clip off the time where we had these external disturbances. So I may want to get an audio. This is the whole audio.
Minister of India is Narendra Modi.
But if I want only the last 2 seconds of it, this is an array. I want the last 2 seconds. So I do -2 into audio.framerate. The total number of entries were the number of seconds into the frame rate. And if I do -2 into audio.framerate, so and then colon. So this is going backwards from the end, going backwards up to 2 seconds. The syntax is the same as the Python list that you might have seen.
Here is Narendra Modi.
So you can notice that this is a 2-second audio, whereas the original was a 3-second audio. So you now have the required set of tools to do such kind of manipulations using NumPy. Any questions? Okay, then there are some other important operations. One of them is reshaping the arrays. So let's say that we had an original array, which is 1, 2, 3, 4, 5, 6, 7, 8, 9. If I print out its shape, it comes out to be 9, comma. So whenever you see 9, comma, or n, comma, you can immediately conclude that it's a vector. The vector is written as 9, comma, or n, comma. Let me again just cut this. Now I have 9 numbers. I could have also arranged them in a 3x3 dimensional matrix. Very often we require such kind of manipulation. So I do this. I create this new array object, grid 3x3. I do reshape 3, 3, which will put 1, 2, 3 as the first row, 4, 5, 6 as the second row, and 7, 8, 9 as the third row. And if I see that, you can verify 1, 2, 3 is the first row, 4, 5, 6 is the second row, 7, 8, 9 is the third row. The shape of this new array is 3, 3. Now it's a multidimensional array. It's no longer a vector, it's a matrix. The number of dimensions is now 2. Right? So there are various kinds of manipulations you can do. You can play around with this and understand more. For example, you could have also done something like just 1 second. So now I have done a weird kind of a manipulation. This is now reshaped. The number of total entries still remains 9, but this is now reshaped into a 3-dimensional object where I have 1 as the first dimension, 3, 3. So you can notice that this is, now you can see that there are these 3 square brackets. Here you had only 2 square brackets. And in the vector case, you had a single square bracket. Sorry, there was a question. Yes. Sorry? Okay. So we can see that this different kinds of reshaping you could have done. You can also see that, so very important is to also try and fail in writing code here. So just try some things and see if those things work or not. So I have this grid which contains 9 numbers. So if I somehow want to reshape this into 2, 5, should this work? Should this not work? What is the number of entries in grid? Original original vector, 9. And if I want to reshape into 2, 5, which means I need 10 entries. So this should technically fail. Cannot reshape array of size 9 into shape 2, 5, which is another very beautiful feature of NumPy, that the errors are very informative. So you can very clearly see that this is the error which is happening. It's often important to try out different failure cases. So you'll get a better sense of the API if you do that. Now, one very common way, in one very common place where you end up reshaping is, let's say when you're trying to do some image classification as a machine learning task. Given an image, you have to tell whether it's a cat or a dog or a human or a buffalo or whatever. So images are, you have already seen, they are represented as either height, width, or height, width, RGB. For simplicity, let's now imagine that the image that is given to us is a grayscale image. So therefore the dimensions are height, width. So you'll be given an image like this. In this case, I've picked up a 28 cross 28 dimensional image. Now when you want to feed it to a machine learning classifier, there they don't want to be looking at images. Typically they don't want to be looking at images. They want to be looking at flattened arrays. They want to be looking at 1D arrays. So therefore, I will have this image of size 28, 28. I may want to flatten it into a 1D array. I can do that using a particular function called flatten, which will give me a 784 comma, which means it's now a vector. Or I can also just get this total size, n equal to flatten image dot size. Size would be the total number of entries, which is 784, and I can just reshape into n. So n comma, which just means reshape into n, and I'd again get the same flattened image. Now, whenever we're doing flattening or whenever we're doing reshaping, there is a very interesting, very nice, convenient thing which NumPy has given, is to use this filler of -1. So whenever we don't know the shape of all but one dimension, we can instead just write to -1. So I want to now reshape this 28 cross 28 image into a single dimension. And let's say I don't know that what is 28 cross 28. It's 784, but let's say I didn't know that. I can just give random 2D image dot reshape -1. And since it's the only dimension for which it needs to figure out the size, it will automatically calculate that this shape should be 784. So it's very commonly used, this reshaping using just the -1 attribute. Let me show this in another way. So now we have this flattened image. So we have this flattened image. You can see it's a 1D array. You can see a single square bracket. You can also see its shape, 784 comma. Now I want to reshape this into a square matrix. For some reason, let's say I know that the number of rows is 28, but I don't know the number of columns. So one of the axes I know, but one I don't know. So I say that take this flattened image, reshape this into a 2D matrix where the number of rows is 28, but number of columns automatically figure out using the -1 syntax. It will then automatically figure out that this should also be 28. So therefore you can see that through running this operation also you get 28 cross 28. On the other hand, you could have also done that I want the number of columns to be 28, but I don't know the number of rows. So you just leave that attribute to be -1, it will automatically figure out that should also be 28. So these are two very nice, convenient things to try out. There are some also very nice functions such as concatenation. If you have an array 1, 2, 3, 4, 5, 6, you can concatenate that to make another 1D array 1, 2, 3, 4, 5, 6. There are other operations such as vertical stack and horizontal stack. So you have 2D arrays, 1, 2, 3, 4, 5, 6, 7, 8. You can see that you can vertically stack them to create. So you have two matrices of size 2 cross 2. You can vertically stack them to make of size 4 cross 2, or you could horizontally stack them to make of size 2, 4. I'll not go in a lot of detail for these because there are endless such number of functions which you can try. But I want to quickly touch upon the other two important things. One is universal functions. The other is aggregation and broadcasting. So I want to cover those first. So universal functions are these vectorized functions which run on element by element basis. So let's say if there is a particular function which we want to run on every element in an array, we end up calling this universal functions or ufunc. We have already seen one implementation of this earlier when I made that matplotlib plot. So I had this X range. I had this X range which was a NumPy array. Now I wanted to apply this function f, which is just sin x, on each individual element. So therefore what I'm essentially doing is to use this universal functions which are applied element wise on each element in an array. You have this a range, np.a range of 5, which gives you this NumPy array of 0, 1, 2, 3, 4. You can perform an element wise multiplication with 2, which gives you a new array y where the entries are 0, 2, 4, 6, 8. You can perform an element wise exponentiation operation, e to the power 0, e to the power 2, e to the power 4, e to the power 6, e to the power 8, which gives you these different values. So therefore these functions end up significantly making things easier for you to write code as well as making it closer to maths. And they're significantly faster than if you were to do the same thing using just simple Python. So there you would have had to use something like, if you were using pure Python, okay, for some reason it doesn't, it's created new cells here. So let's say if we had to do this on our own using a Python list. And you would have done multiply with 2 equal to x into 2 for x and x list. And you could have printed that. You get the same operation, but look at the amount of code you have to write, and this is significantly slower. The other very useful thing with NumPy is that it gives you a lot of aggregations, which is often very useful. So given a data set, you often want to find out the mean, the median, the mode, the sum of the numbers, the minimum of the numbers, the mean, the standard deviation of these numbers. And again, you can get these. Can we please have silence? Yeah, if we want to see these different aggregations, they are these simple functions, np.sum, min, max, given over this data, where this data is this particular NumPy array. Now we could have, let's just check if there are other ways of getting the same thing. So we have data.max. So you could have also used that. Rather than calling np.max of data, you could have also called data.max. So therefore it's up to you to explore the API, figure out which of them are available in this form, np.aggregation of data, np.aggregation of array, and which of them are available on array.some particular function. I typically suggest using these because this is more explicit. Now we come on to a very commonly confused subject of broadcasting. So first we look at this very simple matrix multiplication. you have this array 1, 2, 3 and another array 2, 2, 2. If I do A cross B, you will have this universal function operation which will do 1 to 2, 2 into 2, 3 into 2. So therefore the new matrix, or the new vector that you'll get is 2, 4, 6. So nothing complicated here. The shape of it is 3 comma because it's a vector. Now I can also just write that if I want to multiply the scalar 2.0 with this vector 1, 2, 3, I can also just say that D is equal to A into scalar. Now the scalar is a single number, whereas the A array is a 1D array. But this still gives me the same answer. You can notice that doing A into scalar is the same as doing A into B. And B we had this vector 2, 2, 2. So this happens because of the special property in NumPy, which is known as broadcasting, which allows us to stretch some dimensions when possible. This makes the whole implementation much more compact and is also very efficient, because now you don't have to explicitly store these 3 numbers, an array of 3 numbers 2, 2, 2. Instead, you're just storing a single scalar. So it's much more efficient under the hood also. The way this happens is, let me expand this out for you. So we had this vector A, which was 1, 2, and 3, whereas the scalar B was 2. Right? So the original shape of this is 3 comma, but the inferred shape, especially when we are doing broadcasting for such operations, we will assume that this is 1 comma 3. So it's 1 comma 3 means you can consider it to be like a row vector. So A can be understood to be a row vector, whereas B, or a scalar, was originally just a single value 2. So its inferred shape we can assume to be just 1. Right? It's a single scalar. So now we have various kinds of rules in broadcasting. It will start looking, so this is for some reason not right aligning. Okay. So now you can see that these things are right aligned. So you can notice that this axis for A was 3 elements. This had 1 element. So it will end up expanding this 1 and making it 3 and adding this additional 1, so that it will end up doing something similar to 2, 2, 2, whose shape is also 1 comma 3. And now A and B's shape is matching. So it has expanded out this 1. It saw that there was a 3 here. It will expand it out to make it 3 times, which will make it 2, 2, 2. So now the shape will be considered, we can also prepend a 1. This will become like a 1 comma 3. And therefore now if you can see the element wise multiplication 1, 2, 2, 2, 3, 2, that will give you 2, 4, and 6. So we've looked at some rules of broadcasting. It starts up with aligning the shapes of different objects. And then it starts to see, if I see a 1, it will try and expand that to the bigger number. And if there is an object with lesser number of dimension, it can prepend a 1 to it. Prepend means always prepend to the left. So there is this very nice video which I've also put on. I'll also share this. So these are some set of rules which we will follow. If A and B, if X and Y have different number of dimensions, prepend once to the shape of the shorter. So we did that. Prepend 1 to the shape of the shorter. Any axis of length 1 can be repeated to the length of the other vector's length. So this axis was originally 1. We expanded out to make 3. And all the other axes must have matching lengths. So therefore, if we are trying to do something like So if we now take some x whose shape is 2, 3, and if we take some y whose shape is 2, 1, so then this particular entry we can repeat multiple times and make it 2, 3. So let's perhaps take an example of that. Let's take an example where this addition will happen. X is 2, 3. So 2 rows, 3 columns. 2 rows, x is 2, 4, 3 columns is 6, 8, 5, and 3. Whereas y, this is my matrix, my multidimensional array x, and my y is 2 rows, 1 column. So this is, let's say, 1 and 2. Now if I do x plus y, what will happen? I will expand out this, which was my column, multiple times. To also make it, I will also want to make this 2, 3, and this is originally 2, 3. If I want to expand this to become 2, 3, I will repeat these entry 2 more times so that these dimensions align up. I've repeated them 2 more times to make it 2, 3. And now if I'm doing x plus y, I'll get 2 plus 1, 4 plus 1, 6 plus 1, 5 plus 2, 8 plus 1, and 3 plus 2. So this is how the broadcasting will happen. Let's verify this first in code, and then let's get back if you have questions on this. So we had an x which was 2, 6, 8, 4, 5, 6. 2, 6, 8 and 4, 5, 3. We can verify the shape of x. 2, 3, 2 rows, 3 columns. Whereas y was this matrix or this np.array of 1 and 2. So it was 2, 1 originally, 2 rows and 1 column. You can see that x shape is 2, 3 and y shape is 2, 1. If we do print, or let me call it z equal to x plus y and print z, you can see 4, 8, 10, 5, 6, 4, and we were to print the shape of it also. You can see that the shape of z is also 2, 3. So this is how broadcasting happens. These are the set of rules where we expand out the axis in accordance to these set of rules. Any question in this? Some of these things will only become clear when you practice, so therefore we'll have the lab session where we'll do some practice on this. And now finally, to finish off, we have 2 very simple concepts. One is known as a Boolean mask. Can we please have silence? Can you please do the discussions later? We have this data, which is this numpy.random.random integer between 1 and 20 with a size of 10. I'm masking where the data is greater than 10. So this will give me a Boolean array. I had this set of values 16, 5, 11, 11, 2, 17, 2, 13, 19, and 4. I check which of them are greater than 10. So this mask is equal to data greater than 10, gives me a Boolean array, which is, can we please have silence? This is true, 5 is greater than 10 is false, 11 is greater than 10 and is true, so on and so forth. So we get another vector, another simple array, which is a Boolean array, which is only containing trues and false. So this is also of size as the original one, which is of size 10. Now, very importantly, we can do some kind of filtering on this. So if I do data of mask, it will give me only those entries in a new array where the mask was true. So it will give me where the mask was true, 16 corresponding to this true, 11 corresponding to this true, 11 corresponding to this true. It won't give me 2, it will give me 17, 13, 19. So therefore, this is a very efficient way of filtering out the data. If you didn't use this, if you're using Python list, you could have used the filter attribute, you could have used the filter functional paradigm, or you could have used some simple list comprehension. X, if x greater than 10 for x in range x list, something like in x list, something like that. There are some other interesting functions which are available, which is to sort the data, 2, 1, 4, 3, 5, as well as, so you can do a return a sorted copy, or you can do a sort in place, which will modify the original array. There is a numpy.rsort also, which returns the indices. So you can see these different sort operations. You had this 2, 1, 4, 3, 5. The sorted copy is, if you call np.sort, this is a copy of the original array. You can see that the unsorted array remains the same because it's a copy which is returned while you're sorting, not the original array is modified. But if you were to call .sort, it modifies in place. Okay, so I wanted to end at this point, and it's almost time also.